Welcome back to Math 210. Look, we know exactly why you're here. You're redoing this course, you want to finally master this material, and honestly, you're just ready to put it behind you for good, right? So we are completely skipping the dry, tedious lectures today. Instead, we're giving you the ultimate refresher explainer. We're going to cut straight to the core concepts, the classic test traps, and the absolute best shortcuts you need to know to crush this. Okay, so let's dive right into this. We're breaking the entire course down into 5 highly logical, bite-sized buckets. Classifying your data, organizing and visualizing data, finding the center, measuring the spread, and finally, pinpointing position. All right, section 1, classifying your data. A ton of frustrating mistakes happen right at the very start of the exam, simply because data types get misunderstood before the calculations even begin. So let's build a rock-solid foundation right now. You've got to watch out for this classic test trap. Remember the alliteration here. A population is the complete collection of elements you're studying, and it's described by a parameter. Both start with P. On the flip side, a sample is just a smaller subcollection drawn from that population, and it's described by a statistic. Both start with S. Population goes with parameter, sample goes with statistic. Lock that in your brain. Next up, we need to split our quantitative or numerical data into 2 distinct categories. First, we have discrete data. This comes from a countable number of values with gaps between them, kind of like counting the number of cars in a parking lot. Then we have continuous data. This involves infinitely maybe measured values on a continuous scale without any gaps at all. Think height, weight, or temperature. Seriously, keep this exact phrase from your study notes completely top of mind during the test. It brilliantly illustrates exactly how to tell quantitative data types apart in a split second. If you have to count it, well, it's discrete. If you have to measure it with some sort of tool, it's continuous. It's that simple. Moving right along to section 2, organizing and visualizing data. Now that we're totally refreshed on what kind of data we actually have, let's look at how to properly organize it. Okay, you are absolutely going to be asked to interpret or choose the right graph on your test. You need to know the best use scenarios for these 4 graphs because picking the right visual tool is just crucial for seeing the patterns hiding in your raw data. Histograms are your go-to for overall distribution shape. Dot plots, perfect for spotting repeating values in small sets. Stem and leaf plots are great because they actually keep the original raw numbers intact. And scatter plots are what you use when you're comparing 2 totally different variables. What's really powerful here is how scatter plots instantly answer the question of whether X and Y move together. As you can see, researchers look for a positive linear relationship when the points go up from left to right, a negative relationship when they go down, a curvilinear relationship when they form a sort of arc, or absolutely no relationship when the dots just look like a random, messy cloud. Now, when you're looking at quantitative data on its own, histograms show you the actual shape of your frequency distribution. Is it bell-shaped, skewed, uniform, or bimodal? Notice how the bars actually touch here? There's a reason for that. It's a key feature of a histogram. It uses class boundaries, not just class limits, to make sure there are 0 gaps, perfectly representing those continuous data intervals we talked about earlier. All right, on to section 3, finding the center. With our data visualized, we move to calculating the core metrics, starting with finding that typical or middle value of a dataset. Now, you probably remember how to calculate these 4 measures from the first time you took this course. You sum it all up and divide for the mean, find the middle number for the median, spot the most frequent value for the mode, and just average the absolute high and low for the mid-range. But listen, the real trick to passing your exam isn't just knowing the formulas, it's knowing which one of these to actually trust when you're analyzing real messy data. So when do we use mean versus median? This is the exact kind of conceptual question that trips students up the first time around. If you have a data set, how do you know if the mean or the median is going to give you a more honest picture of the center? Here's the golden rule. The mean uses every single value in its calculation, right? And that makes it incredibly sensitive to extreme outliers. If just one value is massively higher than the rest, it pulls the entire mean way up. The median, however, just cares about the order of the numbers. That means it stays safely grounded right there in the middle, regardless of how crazy the highest or lowest numbers get. So extreme outliers, always go with the median. Section 4, measuring the spread. Because finding the center is really only half the story. 2 datasets can have the exact same mean and the exact same median, but look totally different. So we gotta measure how spread out those values actually are. While the range simply subtracts the lowest value from the highest, it completely ignores everything in between. And that's exactly why we rely on variance and standard deviation. The standard deviation is just the square root of the variance. And because it uses every single score in the distribution and neatly puts the spread back into your original units of measurement, standard deviation is literally the most common, most powerful measure of variability you're going to use. Small standard deviation means your values are clustered and super tight. Large means they are spread way out. Let's see how this all builds into the famous empirical rule. If your histogram shows a perfectly bell-shaped, normal distribution, this rule is pure magic. Ready? Exactly 68% of your data will fall within one standard deviation of the mean. 95% will fall within two standard deviations, and 99.7% will fall within three. You definitely need to memorize those three numbers for test day: 68, 95, 99.7. And that brings us to Section 5, pinpointing position. Sometimes you don't really care about the whole group. You just need to know how to compare a specific, single value against the rest of the pack. We do this using position indicators, things like percentiles, quartiles, and standard scores. Now, your professor posed this exact scenario in the source materials, and it's a brilliant question. Which score is relatively better, an 82 on Section 1 or a 46 on Section 2? You can't just look at this and instantly say, oh, 82 is better than 46. Why? Because you have no idea how hard each test was compared to the class mean or how spread out the grades were. We need a reliable way to compare apples to oranges. The solution? Calculating a z-score. By standardizing both scores, meaning you take the score, subtract the mean, and divide by the standard deviation, we figure out exactly how many standard deviations above or below the average each score actually is. It puts them on the exact same scale, proving definitively which student performed relatively better in their specific environment. Basically, if a z-score is positive, you're above average. If it's negative, you're below. To wrap up your ultimate review today, take a mental snapshot of this cheat sheet table. It summarizes the absolute fastest approaches to calculating your key metrics. Whether you're finding the center, figuring out the variation, or checking for mathematical outliers using the interquartile range, having these rapid-fire methods loaded in your memory is going to save you vital time on the exam. Now that your memory is completely refreshed on the math, I want to leave you with one final thought from Chapter 1. Remember that even perfect calculations, perfect z-scores, and absolutely flawless histograms mean literally nothing if your original sample was collected using a biased method, like a convenience sample or a volunteer sample. Always, always question where the data came from first. So are you ready to step into that exam, spot those traps, and let the true data tell its story? Best of luck. You've got this.